when we have a system represented by an augmented matrix, it's possible that when we reduce it, we end up with something like this, which is different than what we get for systems that have unique solutions. The problem here is that if we translate these rows back into equations, we get a perfectly good equation here, but y is still in there. And this equation, though, tells us that 0 equals negative 39. Well, it turns out that that means there's no solution. And since we have two straight lines here, the only way two straight lines are going to have no solution is if they're parallel and non-intersecting. So if we have a contradiction like this that's totally consistent with the two equations, we know that there is, or with the assumption that the two equations have a unique solution, we conclude that there is no solution. We could also have this situation for these two equations, and if we express it as a matrix and reduce it in the usual manner, we get this. Translating into equations, we get x plus 3 halves y equals 4, the same equation we had here, but 0 equals 0, okay? Well, that's not a restriction, that's a true statement, whereas this is a false statement. This means that there's no restriction based on this, whereas here, this means you're totally restricted, there's no solution. In this case, your solution is the entire line, x plus 3 halves y equals 4, meaning that any pair of numbers x and y that satisfy this will be a solution to both equations. Now the reason for that is fairly obvious. This equation is just a multiple of this one. Okay, so if we solve this each equation for y, let's say, we're going to get exactly the same slope-intercept form. In any case, any point on this line is a solution to the whole system. It's a solution to both equations. Okay. So in one case, in this case, our solutions, our straight lines would, if graphed, would look like this. Okay, these are the, this is the graph of these two lines. Two lines turn out to be parallel, but they don't intersect. If we were to graph these two lines, they would overlap. The lines would be exactly the same, and every point on the line would be a solution to both equations. Okay, now if we go to 3 dimensions where things get a little more complicated, one possibility is that whatever the 3 equations are, they reduce to this matrix. And this tells us then that x equals 5, y equals negative 3, z equals 4. Meaning that the 3 planes represented by the 3 equations, and we haven't talked exactly about how an equation, a linear equation in 3 variables describes a plane, but it does, and we'll talk about this. This says that the 3 equations represent 3 planes, and the 3 planes are intersecting at some point. Okay? This plane intersects this plane along a line, and then this plane intersects that line, and at that point we have our solution, which is 5, negative 3, 4. I'll observe that a single point has dimension 0. We should understand that a point has dimension 0, a line has dimension 1, a plane has dimension 2, and the whole 3-dimensional space has dimension 3. And we'll understand the whole idea of dimension a lot better as we move through the course, but that's sufficient for right now, and that's something you would get out of a geometry course. Okay, now what if the equations reduce to this? Well, that reduces down to the equation x plus y equals 5, z equals negative 3, and 0 equals 0. Well, 0 equals 0 is true, so there's no restriction there. If it was 0 equals something besides 0, there'd be no solution. Okay? So now we have z equals negative 3, x plus y equals 5. What's that look like in 3-dimensional space? That's fairly easy to graph. Well, in 3-dimensional space, z equals negative 3 correspond, well, first of all, the xy plane could just be thought of as like the flat surface of a table with a z-axis pointing up out of that. So we have an xy coordinate system and a z-axis pointing vertically above that, and all 3 points intersect, all 3 axes intersecting at the origin. Okay, if we go to z equals -3, well, here's the z-axis. We go down 1, 2, 3 units, and we have this intercept. And now we have no restriction yet on x and y. So just the z equals -3 equation tells us that whatever else we have, we're confined to the plane where z equals -3, and that's a plane parallel to the xy plane, parallel, say, to your tabletop, but 3 units lower. And we represent that by drawing an auxiliary axis, a y prime axis, and an auxiliary x axis, which we call x prime, which we understand as being 3 units lower than the xy plane in 3-dimensional space. And whatever else our solution does, it's confined to that plane. Well, what else does our solution do? Well, our solution says x plus y equals 5. That is a line with x and y intercepts, x-intercept of 5, y-intercept of 5, in this auxiliary xy plane. So we come down here to the x prime axis. We got the point 5, 0. On the y prime axis, we got the point 0, 5, and our line goes through those 2 points. It stays in this plane, and every point on this line is a solution of our original 3 equations, whatever those 3 equations might have been. Okay, so if our 3 equations reduce to this, and therefore reduce to these 3 equations, that means any point on this line is a solution to all 3 equations. Okay, well, note that that line has dimension 1. A straight line has dimension 1. And we say we have one free variable. Now, I'm not going to explain what that means right now, but that's kind of a terminology you kind of want to have seen, so when I do explain it, you can maybe relate it to this. So you don't have to remember that, but kind of make sure you understand that I've used that term in this situation. Okay? And we also say then that this line is a subspace of our 3-dimensional space. It's a 1-dimensional subspace of 3-dimensional space.